Let's look at an example of using the difference quotient with numbers. You're going to have a couple practice problems in your homework that will ask you to do that. But to sort of convey how this is actually the same thing that we were doing when we were studying average rate of change a few videos ago. So it says find the difference quotient for the following function over the following. Let's say when x is equal to 1 and h is equal to 2. And basically, you can use the difference quotient to actually solve average rates of change. And it's actually helpful to first start plugging in those values. But if x is equal to 1 and h is equal to 2, let's go ahead and just copy out what is the difference quotient on the top of this page. I don't know why I'm using red. Let me go back to black pen. The difference quotient for any function is always f of x plus h minus f of x divided by h. Oops, you can't see what I'm writing. There we go. And so if we wanted to start with it, let's try using the difference quotient to figure out what happens when x is 1 and h is equal to 2. And actually what this will do is it will do the same thing we did a couple videos ago where we figured out the average rate of change between here. Because in the difference quotient, x is always your starting point. So this would be, I'm saying let x be equal to 1. And h is always how far to the right are you from x. So if h is 2, that would imply that I'm finding the average rate of change between 1 and 3 exactly as I did before. But essentially, it's a different algebraic function. So we're plugging in things a little bit differently. So let's just go ahead and do that. So the difference quotient would be equal to f of 1 plus 2 minus f of 1 divided by h2. And basically, this will calculate, again, the same thing, the average rate of change between the points, the secant line. This is exactly the same formula as this formula. And you might be wondering, well, why are we learning these? Well, this one is more useful for purposes of calculus, and we will be talking about this in class during the next live class. But basically, what we'd end up having is f of 3 minus f of 1 divided by 2. And that's exactly the same thing we did before right here. F of 3, f of 1 divided by 3 minus 1. Or at the end of the day, again, we have our formula. F of 3 was 0, and f of 1 was 4. And so we're going to end up with negative 2. Again, all I'm demonstrating here is the difference quotient will give you the slope, but it's not coded to work between 2 points. It's coded to work between 1 point and how far to the right you are. H is how far to the right you are from your point, and x is just your point of reference. And another thing we could do, one of the points of the difference quotient is it helps us think about what if we shrink h? Like, what if we bring these points closer and closer together? What if I check, say, between 1 and I let h be 1? Or let's say I let h be 0.5. Or let's say we're going to take these points and bring them closer and closer together. We could examine the pattern of what will happen as we get closer and closer to 1, which will help us understand more about what an instantaneous rate of change is. So let's just do a few more examples, by plugging in smaller values of h just to kind of compare. And basically we're seeing what will happen as we shrink our window for our average rate of change. As I said, it should get more and more accurate the smaller the width is. So you can imagine as h gets smaller, this should be better approximation to what's going on that interval. So if x is 1 and h is 2, again, this would be synonymous to saying between x equal 1 and x equal 2 if we were doing it the way we did it using the other formula. But, we would just have, well, f of 1 plus 1 minus f of 1 divided by 1. So what we're going to end up with is f of 2 minus f of 1. And it's all divided by 1, so that would just do nothing. F of 2 would be plugging 2 in here. 2 minus 3 is 1. Negative 1 squared is 1. So I'm going to end up with 1 minus f of 1, which we already know to have been 4. And so I'm going to get minus 3. So we get a slightly different rate of change here because we've brought those 2 points closer together. So, I'm changing h to be the value of 1, which would be right here. And so my average slope actually is going to change. And notice that it's not surprising that it's a little bit of a larger number, because here we had an average slope of negative 2. It's a little steeper between 1 and 2, which is reflected by the math. And you can see what's happening as we do this. Now, what if we got it even closer, or even closer? Like, what if we made it 0.1 or 0.01? Or you might recognize this process as taking the limit. If we're making h smaller and smaller, let's say we brought it like literally right to there, what would happen? That slope would be a very good approximation to the instantaneous slope at that point in time. And this sort of methodology can be used to approximate the slope at a singular point. So let's go ahead and do the math. So we'd have the difference quotient is equal to, well, now we have f of 1.1, because we're going to add them together to start with. Oops, 1.1, and minus the f of the x divided by h. That would be our math. So f of 1.1, let's go ahead and grab our calculator so that we can figure that out without having to do the math. So I would have 1.1 minus 3 squared. That would be f of 1.1, and that's going to be 3.61. So I'm going to have 3.61 minus f of 1, which we already know to be 4, divided by 0.1. And that should give me the slope of that much tinier window. So if I go ahead and divide that, I need to subtract 4 and then divide by 0.1. But that would give me an average slope of negative 3.9. And again, as we get closer and closer together there, you can see that it seems to be getting a little bit steeper. But the question is there a limit to the slope, and what would happen as I get closer and closer? And you can see how limits kind of play into this in the math of why limits are crucial. But let's go ahead and take it another step further. What if we get it like really, really close to 0.01? And you could keep going further and further if you want, but what we can start to guess is, well, what's the limit of this as h approaches 0? Which, spoiler alert, that is the definition of the derivative, a very, very important concept for calculus. But let's plug in 1.01 minus f of 1 over 0.01. And again, how I'm doing this is, again, it's always f of x plus h. I'm using this formula. So I'm adding these two together here, x plus h, minus f of x, and then just dividing it straight up by h. So f of 1.01, that'll be, again, starting with the function 1.01 minus 3 quantity squared, because that's my formula. And here this would give me f of 1.01 is 3.9601. That's going to be minus f of 1, which we already know is 4, divided by 0.01. So if I take that, take away 4, and then divide by 0.01, what happens? And this gives me negative 3.99. And not coincidentally, we see that it's the trending pattern of what happens as I get closer and closer to an h value of 0 has a particular limit. You could probably guess that this is approaching negative 4, and you'd be exactly right. That is actually what we refer to as the instantaneous slope at 1. As you get closer and closer, the slope will get closer and closer to another value. And often we call that the derivative. That's what we're going to be studying for the next few weeks. All sorts of different shortcuts. Because as you could probably agree, this is super, super tedious. And we don't have to do it this way ever. But this it's fundamental to understanding the idea behind what a derivative means and what it's doing. It's calculating the slope at a particular point. And we can always envision it getting closer and closer together by imagining the limit of the difference quotient. So a totally different strategy is figuring out, instead of plugging numbers in, because this is takes a bit of math and is tedious, what if we just plug in f of x plus h algebraically speaking? It's much simpler than having to do the math every time. We'll do that in the next video because this one's getting a little bit long.